So the higher level algorithm is presented in this image. So we will be describing it in details below. So first of all, what we have to do is to detect a flat surface. First, we obtain a canny image of our first image, and subsequently we XOR the canny image with a circle of the maximum diameter of the base image. Then we'll be applying exact Euclidean distance transform to the image. This will give us a gradient image, as we can see here. So we can see that the brightest spot indicates the location furthest from any edge surrounding it, which is the here. So it actually reflects the center point where we will apply our advertisement image. This is successfully applied to all three videos. So the next step is to implement the feature extraction and matching. We implemented shift as indicated by name. It is immune to scale and rotation. We also implemented orb and akaze. Orb is very fast and close to real time, but it fails to solve the problem of poor scale invariance and also bad lighting. Next one is akaze. Akaze is the most current algorithm in implementation, and it is much more superior to kaze in terms of the performance and the speed. The next step is to perform the feature matching by using L1 norm or L2 norm for string-based descriptors such as shift and akaze. We apply Hamming distance for binary descriptors such as akaze and orb. Then we'll be further removing incorrect matches in our homographic calculation by using random sample consensus ransacked. This is implemented using OpenCV find homography function using 5.0 as the maximum allowed projection error. So the resulting homography will be used to be fit into the warp perspective functions. The next one is performance analysis. So we can see that orb and fast perform negatively on scene 2 and 3. In some frames, the image projections goes completely distorted. In low light conditions, it also doesn't perform well. Shift and akaze, on the other hand, produce the most consistent result, even on the two negative results presented in figure 3. So you can see here the left image, which is the result of applying akaze. It works well even with a moving blue car here. So although the shift and akaze provide the most robust result, it is far from running in the real time. As we can see here, it is run on 2013 MacBook Pro Intel, which is an outdated hardware. So to improve the result, we can greatly improve the speed of execution by running the program on newer hardware and specifically running it on the GPU. From the software perspective, we can also compile OpenCV akaze with modifications to run on GPU supporting CUDA. We can also create a multi-core, multi-threaded pipeline that will spawn multiple threads to process different frames for the feature detection, since this is the bottleneck of the real time, as you can see from the table here. So when the homography is doing the calculations, other frames has been calculated in terms of the feature detection to be fit into the homographic calculations. With the combination of these two changes and improvement, I'm sure it will reach